Hello and welcome to my class. I'm Grolin Annesley from ThinkMo Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 5834444290. Today's topic is packet forwarding process, routing basics, and static routing. I left you a homework last class. Let everyone do an experiment of data forwarding across network segments. Before starting the lecture, let's first do a basic review of the content of the previous class. Let me explain to you from the data forwarding process. Let's look at this picture. Actually, it's similar to the lab assignment I gave you last class, except the address is different. Host A here have an address. Then the router side is the gateway of host A. The address of the right interface of the router is the gateway of host B. If future host A to send data to host B, this is equivalent to a data access across network segments. The data will be sent to the gateway first. But what we are discussing today is not ARP. Let's review the overall data forwarding process. For data, when we were in the first class, learned the overall encapsulation of the data. Data is sent from the sender to the receiver. When it is processing data between the two, what kind of relationship exists? Let's first look at the process of data forwarding. Let's start with 4 layers. The first lesson, OSI 7-layer reference model. Then the upper 3 layers refer to application layer, presentation layer, session layer. These 3 are combined into one big application layer for TCP/IP protocol stations. As a network worker, let's talk about the next 4 layers. The application layer now produces a data. Then you will first reach the 4th floor. That is transport layer. Encapsulate. In this picture, here you can see a data we send. A destination port number is identified here. When we talked about the model, I told you 4 layers have 2 protocols. One is TCP. The other is UDP. A destination port will be marked inside. Before we talk about this picture, I want to draw a picture. Okay. Let's talk about this in detail. When data is being sent, why exactly is it carrying a port number? For example, now there is a device on the left. This is a host. On the right there are multiple servers. We draw multiple servers here. Then go to multiple servers in the future for corresponding data access. Now here is a line. There are 3 lines here. Connect separately. This is just a simple schematic. Does not mean that the real network is like this. First make an address plan. Let's say this is 192.168.1.1. Different ports correspond to different applications. In fact, Cisco content designs overall curriculum. For the transport layer, very little is said in the NA stage. But I think if we don't talk more, you may not understand. So let me explain in detail. This is a PC on the left. On the right there are 3 servers. Suppose this is WeChat. This is YouTube. This is WhatsApp. Now I want to log into these 3 apps on this device at the same time, whether it is a mobile phone or a computer. That is, I want to access the 3 servers corresponding to them. So now I ask you a question. If the host now sends them a data, can this data reach the peer? We do not consider data forwarding across network segments today. And the problem of forwarding on the same network segment is based on address. Is this data available now? For example, now access 192.168.1.2 from 192.168.1.1. Data can be sent. That is, based on what we learned about IP addresses, to this position. There is actually no problem with the exchange of visits between addresses. Data can come. But we're going to see what is the process of sending data to the past. If you want to access WeChat from 192.168.1.1, just send a data to 192.168.1.2. If you want to visit YouTube, just send data to 192.168.1.3. Access WhatsApp words. Just send data to 192.168.1.4. This is not a problem. According to data communication, this data can definitely pass. Find the address of the server. Forwarding through routers in the middle. Just send it. But between the data, the principles of data communication we pay attention to. What is called data comes and goes. A sends a data to B. B has to reply a data to A. Just like the ping mentioned in the last lesson. An ICMP request message is sent. The peer needs to give a reply. It's called data communication. PC now access WeChat. It's looking at a certain data in it. The PC initiates a request to WeChat. WeChat needs to reply to the PC. Then when replying to the packet, there is going to be a problem. How to reply the packet? When replying to a packet, the order is like this. I write it out for you to see. We just change the position of it. The 3 destination IPs become the source IP. The 3 source IPs become the destination IP. When the data comes back, it looks like this. WeChat wants to reply to this device. YouTube has to give it a reply too. WhatsApp also has to reply to it. Now the data is back. But for the current device, it received data from 3 different places at the same time. They are all different servers. But they all return to this device. If the device has only one IP address as an identifier, then here comes the problem. How exactly does the device now find? Now what application does this data correspond to? For WeChat, the device initiates a data request. WeChat replied to it. No problem. That for the device. Received from 3 servers at the same time. Reply to its data. Then please. Is this data from WhatsApp or WeChat? Is this data from YouTube or WhatsApp? I can't say now WhatsApp to device data. Put it in WeChat for processing. So for 192.168.1.1, it is now time to differentiate and measure. How to distinguish different application services. Communication based on IP address now. It can only achieve host-to-host communication. That is, sending from one host to another host. Nothing more. That's on the host. I want to run multiple applications on one device. Implement multiple services. Application-to-application communication. It can't be achieved. Now relying solely on IP addresses. There is no way to handle it. We're going to use the transport layer to process. Then in this picture, the transport layer we wrote. It writes a destination port called 80. This is one of the port numbers that everyone is asked to memorize. In the transport layer, first of all, it realizes end-to-end communication. It is different from the 3 layers we mentioned. IP addresses only enable host-to-host communication. End-to-end communication. In fact, it is application-to-application communication. So this is the transport layer. So how does the transport layer implement it? With a parameter called port. Then please pay attention. This port number is a logical port. That is, it is not a tangible. It is a logical port simulated by technical means. For us, the port is based on the host. An application-level concept. Different ports correspond to different host applications. Then here, we're going to make a modification to it in the diagram. That is, based on the network layer. The transport layer can implement a virtualized port. Use these different ports to locate different applications on the host. For example, now this host has downloaded 3 applications. Connected a WhatsApp, a WeChat, a YouTube. Make an identification. Suppose this is WeChat. This is YouTube. This is WhatsApp. Logically speaking, we don't know. What is the relationship between them? That is, there is no port number to differentiate. For example, WeChat port is 100 locally. YouTube port is 200 locally. Of course, when I tell you about real communication, these ports are not available. These cannot be used casually. Then the port 100. Right on the PC. Identify the WeChat app now. Then 200 identifies YouTube. Future. When the device is in data communication, it will carry these parameters. Please pay attention. This is the reply packet. This is the message sent. In it, we'll add something. For WeChat, when the device accesses 192.168.1.2 locally, it will carry the local port number of 100. It will be preceded by a logo. Is a colon. Represents this data communication. Initiated by local WeChat. Certainly. The peer does not care what your local port number is. So what is the use of this port number? The data sent by the device. How many ports? For WeChat server. It doesn't matter. If many devices access the WeChat server in the future. How to distinguish? Based on the TCP protocol. You will learn in subsequent advanced courses. TCP will communicate with some other clients. This is called the server. The server is called the client. If the connection is based on TCP, there will be a unique identifier for the session. That is, establish a TCP connection. On the server side it is unmistakable. That is, WeChat is now establishing a TCP connection with the device. Then this port number is actually, it's not there to help it with data differentiation. But when the data replies to the data packet, reach this device, it knows that it corresponds to the program on the device. This is for the initiator. A more meaningful port. Of course. Data communication. Address-to-address exchange. Then if it comes with the port number, it also needs to find the port number of the other party. So now for the other party. Assuming their port numbers can all be the same. For example, they are all port 1000. Now for data communication. In fact, it is accessing its 1000 port. The same is true below. I wrote the same mainly for the convenience of copying. It doesn't matter if they are the same or not. If now go to visit 3.100. It is a local YouTube to initiate. That is 200. Let's visit here. Further down is 300. For us now. During data communication. When data is sent. That's how it's sent. Local 1.1's 100 to find 1.2's 1000. 1.1's 200 to 1.3's 1000. The data came like this. Then when the data is sent now, it is necessary to respond to the corresponding data packet. Then when the data packet is replied, it will be different from before. It's not just address to address. Instead, Add the port from the address. Reply together. That is, when the reply packet is sent again, we will put the overall source IP and destination IP, plus source port and destination port. Swap all. Let's see now. Now WeChat, YouTube, and WhatsApp all reply to PC. Then when the device receives this data, can it differentiate between different applications? Not just now. Because there is only one address. It does not distinguish between applications. But now it's okay. It received a data. If you are accessing port 100 of the current device, it knows that it is WeChat data. The data that was indeed sent to WeChat just now. What is sent is the port carrying 100. So, if there is a data reply in the future, the access is the local port 200. It knows that this is YouTube data. And then sent to the upper level. Apps like YouTube for processing. So this is the overall logic of data communication. That is, when we exchange data, instead of just taking one IP address and sending it over, instead use the port corresponding to the application plus the IP address. This combination, data communication together. For the peer device, communication and visits are equal. This is data communication. What I told you here. We will intervene in 4 layers in the future. Actually, more is to pass the application data of the upper layer. Speaking of this, you may be a little curious. During class, let's just look at the ARP message. It seems that there is no TCP in it. We have a lot of agreements. It works at different levels. What we learned about the transport layer. It is more for the application of the upper layer to serve. That is, future. You will be exposed to all kinds of real business data. Then in each business data, it is all identified by the transport layer. But the ARP we learned, you can think of it as a small function. ARP is a layer 2 protocol. Let me tell you about our verbal addressing habits. This is ARP. This is E2. Followed by the frame end of E2. The front is its frame header. The upper layer of ARP has no content. Actually, the question you want is, the device now wants to send a data to the peer. It is 1.1. It is 1.2. Assuming they are directly connected. Same network segment. The device is now going to send data to it. Because the device does not know the MAC address of the peer. The destination MAC of its data link layer cannot be encapsulated. I send an ARP now. Go ask what is the MAC corresponding to this 1.2. Before the device sends this ARP packet. Actually, data encapsulation cannot be completed. That is, before the device finds the peer MAC. It has no way to pass the application data it really wants to pass. So we can only use a small function first. It's ARP. It's more like a functional protocol. Then, for such an agreement, it has a very clear purpose. This message is sent just to request MAC. Then after replying, when sending data, this is the complete data package. Second floor. 3 floors. Source IP and destination IP. The 4-layer assumption is TCP. This is WeChat server. The device wants to access a certain port in the WeChat server. Then it will carry the corresponding port number here. Then there is the application data. For example, if I write a sentence of hello here. These are 2 completely different types of data communication. ARP is a functional protocol that requests a MAC address. And when the device finally delivers the overall data, it will complete all the data encapsulation process. The transport layer locates applications based on ports. The exchange of visits between communications is peer-to-peer. Then for PC. Received data. Applications can be differentiated through different ports. This is a port-to-port exchange. So there are some caveats you must know. First, the transport layer. It has a port number. Transport layer ports. It ranges from 0 to 65535. You will learn a lot in the future. This number you will be very common. This is the total number of ports. That is, whether we use TCP or UDP in the future. The total number of ports in our transport layer protocol is such a value. Then each port can uniquely target a service. But not every port is quite random. Not every port is strictly regulated. Instead, it is between 0 and more than 60,000 ports. Some are clearly defined. Ports from 0 to 1023 cannot be used at will. Ports 0 to 1023 are called well-known ports. It cannot be used casually. This is a port reserved in advance. For example, the local wants to initiate a service request now. So now I'm going to turn on an app service. Assuming this is a network device. I want to telnet into this device. Everyone should know. One service all over the world. If you use more, appear more frequently. That means everyone in the world. Just go online. Or when debugging the device. Often use a function. And this feature has been developed. Then make a clear rule. Reserve these port numbers. This port will be dedicated to it in the future. That is, I can name it. Then this port number. Specific to that service. Then for TCP. Although it will not be covered in detail in the NA stage. But you need to know it. It is a connection-oriented protocol. This connection is a logical connection. It is a more reliable protocol. Because it can, based on when the data is sent to the peer, you can make a confirmation to its corresponding source device. That is, by sending and confirming such a mechanism, to ensure that each message is sent to the other party. It's very reliable. There are some ports in TCP. Is what you have to remember. For example, in this picture, have a port. Everyone can see. Destination port written here is 80. If the host sends a data now, send to peer. I want to access port 80 of this device. Then now, the host is accessing the HTTP service of the peer. This service is a well-known port. Is 80. HTTP is an unencrypted web service. Then there is HTTPS corresponding to it. It is port 443. That is, if the host wants to access an encrypted web service at the peer end, then it accesses the port 443 of the peer. This is called a well-known port. Many people in the world now are using such ports. So make a clear definition. So in the future we are at the end of the NA stage. We'll also show you. I will teach you a remote management method. Telnet. This is also a TCP service. It uses port 23 in TCP. Is an unencrypted remote login. There is also an SSH. It is port 22. This is an encrypted telnet. The final data is relatively. Confidentiality will be stronger. So I ask you to, at this stage, to have a basic understanding of them. Because we will learn later a lot of content related to them. Okay. But in the basic course, just have a basic understanding of it. Let's take a look at the TCP encapsulation. Now when encapsulating at the source, access port 80 of the peer. If the peer I want to access is Google, I'm going to go to Google's web service. 4-layer encapsulation. Then write a 1027 locally. This is randomly generated. That is, for the source end of the current device. It is possible to generate a random port locally. Then this random port must be greater than or equal to 1024. Then locally initiated. May be greater than or equal to 1024. All the way to port 60,000. Any port between. As native device only. Differentiate between different ports. After 4 layers of encapsulation. Start encapsulating 3 layers. Let's take a look at its content. I'll take a screenshot of this picture. This is the overall data access initiated by. Now the 4 layers of encapsulation are complete. To come to 3-layer encapsulation. Because source device encapsulation is from top to bottom. So let's look at the encapsulation of the IP layer. Now the source device is 1.1. The source IP is yourself. The destination IP is 172.16.10.1. 3 layers are packaged. Very simple. Then I will not fill in the other parameters. Certainly. There will be a protocol in the 3rd layer. Indicates that the upper layer is TCP. This is when data is received from that device. But today we only discuss its address and port. Some core parameters like this. Now I want to ask you a question. If after packaging, logically speaking, 3 layers of equipment installed, you know they are not on the same network segment. Now combine the ARP mentioned before. Think about it. How does host A know whether the other party is in the same network segment as it? Okay. Host A calculates with its own mask plus the IP address of the other party. Get its network segment. And compare with yourself. If it is found that the destination is now crossing the network segment, it still has to make an ARP request. But do you remember? If theoretically they are directly connected, is the same network segment, host A directly sends the ARP broadcast to request the MAC address of the peer. The peer will reply when received. But now because they cross subnets, ARP is a broadcast packet. If you still send a broadcast to request its address, this broadcast packet cannot be transmitted from the right interface through the left interface of the router. So now when host A requests the MAC address again, the MAC that is actually requesting the gateway. Now, it is time to send an ARP broadcast request to the MAC of the gateway. Please pay attention. Once involved in the host to find the gateway. Then actually intervene. The routing layer we are talking about today. That is encapsulated IP. It is found that the source IP and destination IP are not in the same network segment. The process of the host to find the gateway. In fact, it is a routing process of the machine. The realization principle of the gateway is equivalent to the host here. Wrote a root entry to go anywhere, pointing to the router. But for us, is pointing to a gateway on the host. But in fact it involves the function of routing. Data is sent to router A here. It needs to query the corresponding routing table. Help us with data forwarding. This process is called the routing process. When the host is actually accessing now, we'll go to the gateway first. The configured gateway is 10.1.1.254. It looks for 10.1.1.254. Let it help itself to find this 172.16.10.1. On the contrary, if they are on the same network segment, host A will not find the gateway. So after the IP layer is encapsulated, after the source IP and destination IP are determined, actually, the most critical decision is the encapsulation of the second layer. After 3 layers of encapsulation, we will definitely check whether the source IP and destination IP are in the same network segment. If in the same network segment, it means that the second layer is the address of the encapsulated peer. If not in the same network segment, it means that the destination MAC of the second layer encapsulates the address of the gateway. Here on the third floor, as long as two people are on the same network segment, Layer 2 encapsulation is the peer. If not in the same network segment, Layer 2 encapsulation is the gateway. This is a basic logic of data communication. Okay. Next we review ARP. Find the MAC of the next device through the cache of ARP. That is, if I've sent the corresponding request before, there will be a MAC with a gateway locally. The cross-network segment is actually sent to the gateway. If not found now, host A wants to send an ARP request to request the MAC of the gateway. These we have learned in the last lesson. Let's look down at the two-layer packaging. That is, encapsulation of Ethernet, purposeful MAC here, source MAC, and type. There will be a field in type. Indicates that the upper layer is the IP protocol. For the current overall data, the MAC of the gateway and the MAC of the peer will fill in here. The source MAC is always the host's own MAC. This is always the case when host A sends data. The MAC of the gateway will be encapsulated here. Then let's make a brief summary. When the data is sent as a whole, just like host A sends data to host B, let's first analyze the four layers. Suppose a port 1027 is written locally. The host accesses port 80 of the peer to access the web service of the peer. Then when the final peer replies to the host, it is from port 80 of the peer. Reply to port 1027 of the host. This thing can't be changed. The host accesses the web page of the peer. Of course, the web page on the other end will reply to the host. The local host is the peer to access on port 1027. So when the peer replies with data, port 1027 cannot be changed. If change, the host cannot find the service corresponding to the request just initiated. So when performing data communication, source IP and destination IP, the source port and destination port are only exchanged, but not modified, including forwarding no matter how many devices in the middle. It cannot be modified during the entire data transfer process. The port number will not change. Secondly, let's look at three floors. In the third layer is the IP. The host's 10.1.1.1 accesses the peer's 172.16.10.1 per arrival to a device. Must be queried on this device, corresponding to the appearance of the destination. Although we haven't gone into detail. But first of all, you must know the principle. Certainly. The same is true for reply packets. Let's think about a question first. Port redirection. Will the ports be modified? The analogy we just made. You can think of it as if you are sending a courier. Let's say I'm in region A. I want to send a courier to area B. Then my courier, recipient and sender information. It cannot be modified in the middle. Once modified, when data is sent over, that is, when the package is delivered, peers have changed. Data communication. I also told you in the first class. The difference between a MAC address and an IP address is that the MAC address is like a transit node in the middle. Those transfer stations are often changed. When host A is sending data, the current destination MAC is the MAC of the gateway. After the request, actually from the local MAC address AA, send to gateway MAC address. But when the router assists in data forwarding communication, router and host B perform data encapsulation. The package is the MAC of the 01 interface. Send to peer. Here is BB. Of course, ARP requests and replies will also be performed. The router receives the ARP request. It replies to host A with its own address. Query routing table. This is a direct route. It will also send. When sending, the route also has to request the MAC of host B. You will find, when encapsulating data, the MAC address encapsulates the destination MAC of the current data. Since the working range of the MAC address is under a broadcast domain, different interfaces of the router are different broadcast domains. That means, once the data crosses the router's interface, the MAC address encapsulation will definitely change. Because the MAC address of the second layer actually work under a broadcast domain, or work on a link. Then in here, every layer 3 interface passing through a router. That is, the interface with IP is now configured. It's all MAC. Every interface. When we finally go to send the data, the second layer will be repackaged. Then this encapsulation process. It will become the source MAC and destination MAC on each link. It will change. So everyone should know. When data is packaged, the fourth layer is always the same. The third layer is always the same. The second floor is always changing. Broadcast domain. Each link crossed. Each layer 3 interface spanning the router. The MAC address encapsulation will change. Then when the whole is sending data, IP and MAC always work together. IP achieves a positioning under the global. MAC is accurate to each link. Complete accurate forwarding. This is a synergistic relationship between them. Okay. Here's a recap of what we did in the last class. Next we're going to talk about routing. To us, have an autonomous system. In the future, you will be in the CCNP stage. When you come into contact with the BGP protocol, will come into contact with the concept of autonomous system. The autonomous system was originally a concept in BGP. Since the concept is so useful, so it was taken out separately, including when we talk about dynamic routing protocols later. We'll also differentiate. It is also defined by the autonomous system. Scope of different dynamic routing protocols. You have to be clear. This is a concept in BGP. But this agreement cannot be discussed in the NA stage. This thing involves the problem of the overall networking architecture. Without exaggeration, many students who won the IE certificate may not be able to know what an autonomous system is. So let me give you a simple analogy. Let you first understand this concept simply. The abbreviation of autonomous system is called AS. It's a concept on the web. We must be inseparable from the public network to learn routing. Because routing is basically running on the public network. Knowledge exchanged only within the enterprise. E.g. VLAN. There is a protocol running on the public network called BGP. It is very typical to use the number of the autonomous system. You can understand the autonomous system as a network system. Can also be understood as it is a network architectural problem. Then usually a unified manager. The network to build. We call it an AS. This is its basic concept. Then usually within an AS, we'll run the same protocol. This protocol is a dynamic routing protocol. And the strategy is relatively simple. That is, in the future, you will operate and maintain a set of enterprise networks. Then you must plan ahead. For example, some functions that enterprises must implement now. Some gateway configurations to be performed. Configuration of some strategies. Some controls. Configure an ACL. Etc. All the technology you use. Strategy of use. Relatively speaking. It is relatively simple. It's all just to serve the enterprise now. That is to say, now you maintain these 5 or 6 routers in your company. Built a network system like this. It can be said that you maintain an AS. So as is just a title and representative. From our point of view, we can say, a network system built by myself is an AS. But actually from the perspective of the whole world, 5 or 6 routers are an AS. So if this is operator A now, it is also an AS. Our devices need to be interconnected. There are a lot of equipment. Various strategies. There are also various configurations. Then I will maintain the network of operator A. Also an AS. Then the same. Let's say this is carrier B's network. It is also an AS. They also have a lot of equipment inside. There are many configurations. And the network management involved are called an AS. But they will apply for an AS number separately. For example, carrier A is AS 100. Carrier B is AS 200. This is the AS number they applied for. To us, a small AS defined is called a private AS. This is called a public AS. AS maintained by yourself. The outside world is not recognized. But for these AS running on the public network, they have real value. Even if you maintain a router at home, it can also be said that it maintains an AS by itself. It does not matter. Because this kind of thing is not recognized by the outside world. But conceptually it can be called like this. Public AS requires a separate application. Here's the difference between them. You first need to know. Actually, when we go to data communication now, assuming this is a one-by-one business, the egress of the enterprise is connected to the network of operator A. What we are using now is the network of operator A. We can also connect to operators in other countries. For example, they are AS 300. Then they will also interact with each other's data. The configuration of each other's routing protocols will also be performed. Also run some dynamic routing protocols to help the construction of network communication. It's just the internal protocol it runs. Basically the same as us. All in one AS. But they also run other protocols. These will be put in NP. Now there are 5 or 6 routers in the enterprise. It is here to operate and maintain. Then this is actually a private AS. Only. It does not connect with things on the public network of operators. Nothing more. But its concept. We'll talk about dynamic routing protocols in a minute. We'll revisit this concept. So here we must first have an understanding. Okay. Let's move on. We're talking about overall broadcasting. So now it's time to discuss a question. When we network based on switches, its actual network range is very small. The scope of the broadcast is under a broadcast domain. Then it is actually a network segment. Or, when we learn VLAN in the future, dividing VLANs will also have different webcast domains. So the network segment is not accurate. Let's just say it's a broadcast domain. Then it stands to reason. For example, now I have a broadcast data frame. Purpose MAC all 1. Written in hexadecimal is all F. Is a broadcast frame. I can flooding in the second layer network. Then the largest area of flooding is a broadcast domain. Now communicate based on the second layer. Only within this range. ARP we learned in the last lesson. It is a broadcast. This data is sent to the router and it is gone. Data forwarding is not possible. Then if you want, data goes from this device to this device. Now if the data gets here. If only communication within the broadcast domain is used. This data is impossible. We're going to pass the routing function. Just like the cross-network segment access I mentioned just now. As long as the host finds that the source IP and destination IP are not in the same network segment. It is now the process of finding the gateway. Is in the process of routing. This is the same. Data is now going from a broadcast domain to another broadcast domain. Then it is impossible to communicate directly. Must rely on the routing function of the router to help us communicate. So this will involve the concept of routing. Today I will simply explain these pictures around. When a data reach this router RA. When the data comes, each layer of data is encapsulated. It first needs to see if the purpose MAC is looking for it. If not, it discards. The principle of the second layer is: first check whether the target MAC is for yourself. Deal with it if it is. If it is a broadcast, also handle. If it is a multicast, also handle. After watching the second floor, just look at the third floor. For example, data is going to this router RD. Then RA will think about it now. RD wants RA to help it forward data. It's going to find this router. But RA doesn't know where this router is now. Unable to forward data for RD. If possible, RA will help it. If not possible, then RA will discard the packet. What we said. Is there any information about the destination network segment? We call it. Is there a routing entry to the destination network segment? We will focus on this routing entry today. Before talking about routing, let's review the simplest data. Two devices. They are on the same network segment. We call such a device connection as direct connection. Then the future network. Certainly not all devices are directly connected in pairs. In the future, there will not be only two adjacent devices for data communication. It's not that once the device is crossed in the middle. It's not a direct connection. The communication between them will rely on the function of routing. Because it is directly connected, they can communicate directly. This is the first concept we covered. The concept of routing. So if there will be multiple devices in the future, the data is going to the destination network segment. After passing through other routers along the way, then the data is sent. Will be on this router. To query a local representation. Routing table. According to the route 1 by 1 in the routing table. Direct data forwarding. This is the concept of the routing table. Now any layer 3 device. It doesn't have to be a router. It can also be a layer 3 switch. Firewall. All okay. The third layer refers to the network layer. In the future, when addressing and forwarding. Forwarding based on destination IP addressing. Addressing. We will query the routing table of the device. Data forwarding based on routing. Specific addressing. The specific address forwarding is based on routing. So let's see what the routing table looks like. This is what the routing table looks like on a Cisco device. No need to check every time the routing table is displayed. For this thing, enter show IP route on the device and it will come out. This is one of its commands. Let's take a look at the above part first. These are some code names. You don't have to watch these every time. For example, if you want to see this route, in front of this there is an O. You don't know what this is. Look up. This O stands for OSPF. This C stands for connected. This is one of my direct connections. That is. This thing is a reference table. Just to save some characters of numbers. So no need to watch it every time. Here is the routing table. Then, in this table, there are a few important points that need everyone's attention. OSPF we will talk about in NA. Connected we will also talk about. D stands for EGRP. We will also talk about this. L stands for local. S stands for static. These 5 are the ones we will be exposed to at this stage. Let's take a look at the contents of this table. First, look at the first line. You don't need to pay special attention to this kind of thing. This is a collection of main class subnets. This 1.0.0.0 represents a subnet. Actually, you don't need to read this line. When we learn data to guide forwarding, don't need to pay attention to this thing. Let's look directly at the next line. This is the real routing entry. Let's parse a routing entry now. Let's look at this one. This is a piece of information in the routing table. I just said. This O stands for OSPF. This data is learned through OSPF. Learned means automatic. We'll get to OSPF in a minute. It is a dynamic routing protocol. Now this position of O. It is used to identify what protocol is used to form the destination network, or how the destination network is formed. It is now formed through the OSPF protocol. Okay. I annotate it. This is O. Then look down at 1.1.1.1. This is the destination network. Now this network and this route go to 1.1.1.1. I will give you a simple example. For example, there is now a routing table on this device. There is a route tune in it. Is 1.1.1.1. Then if there is a data in the future to RB here, it is going to 1.1.1.1. It happens that there is 1.1.1.1 in the routing table. You can help it forward accordingly. If the purpose of RA is to go to 1.1.1.1, but there is no 1.1.1.1 in the routing table, then this data is discarded. So this is called the destination network. Then everyone will notice. It writes 1.1.1.1 here. Its form seems to be different from the network segment. Can you see it? Students? It seems to be different from the network segment. It seems to be going to such an IP address. Everyone will find. This is an exact IP address. It is not an expression of a network segment. Here you will see 12.1.1.0 bar 24. Those with a bar 24 on the back represents a network segment. For what we say now, the bar 24 means it is in the 12.1.1.0 network segment. These are the 2 forms of routing. That is, classification of routes. In terms of its scope, there are 2 types of routes that appear in the routing table. Segment routing. Network segment routing is the network number. Network segment plus mask. This form is called network segment routing. There is also a route called host route. What we see now. It is a very standard host route. It is an exact host address. This is called host routing. Then this route can only represent one address. And 12.1.1.0 represents the entire network segment. Let me explain the difference. For example, this is a routing table on a router. This is a router. A data is sent to this device, going to 12.1.1.3. Then please pay attention. It can match this route. Then send it out through the 1.0 interface of the current device. But for 1.1.1.1, it represents an exact IP address. If a piece of data is to be sent to 1.1.1.1, can help forward. If data is to be sent to 1.1.1.2, there is no corresponding route here. Just don't forward. So the network segment covers 12.1.1.0. That is, in fact, all addresses from point 1 to point 254 can be forwarded. This is called segment routing. This is the routing table we're talking about. Some basic concepts of it. This is called the classification of routes. Okay. Let's move on. Here is a 110 to. 110 refers to the administrative distance of the routing protocol, followed by a 2. It's called routing metric. Routing metrics are also called cost. It has many names. And then there is a via. 12.1.1.1. This is the address of the next hop. Let's take it as an example. For example, now a piece of data has arrived on the RB device. The data is going to be the address of this interface on the destination router. Now query the routing table to find. It has the address to the destination router. So RB will help with data forwarding. Then when forwarding, need to specify the destination IP of the next hop, because it involves future requests to ARP. That is, after this data is sent out, which interface address should be sent to. This is what we call the next hop. It's just that after this data is sent to the left interface of the router. That is, the left interface of RD. This is called the next hop. The interface that the data needs to arrive at when leaving the router. The address we call the next hop, or the address to be reached. The places marked in yellow represent different parameters. Look down. Here is a 000059. Let me tell you this briefly. You don't have to remember. This refers to the time when the route was learned. It's not important to us at this stage. Further down there is a fast Ethernet. This is the fast Ethernet port. Ethernet is a common 10M interface. Fast Ethernet is a 100M interface. Its bandwidth will be larger. Then in here, F10 is an outgoing interface. That is, now when this data goes out, go out from an interface of the device. This data is sent to the next hop address. Which interface should the device send out to reach the next hop? The number of this interface is the outbound interface, called F10. This is the full picture of the overall routing table. I'll make a supplement to you. There are two ways to form the next hop address. The first way is to manually specify. This method is called static routing. We will learn dynamic routing later. That is, we can use the agreement, automatically generate the next hop for it. This is called dynamic. We'll talk about the difference between the two. I now ask you a question. There is now a routing table. Why sign the protocol? For equipment. As soon as the data arrives on the device. Is there a 1.1 like this? Why do you have to identify it? How was it learned? Does it have anything to do with the overall learning process? I'll give you a simple example. For example, there are now 3 devices. Connect them first. Assuming that the routing table of this device is, there are 2 same routes. If there is a 12.1.1.0 now, 30-bit mask. This is a local direct link. But for this device, I can also configure some static routes on the device. Like now, the device learned a route through the direct connection. Also via 12.1.1.0. Also a 30-bit mask. A route is also written in a static way. Then this is the local direct route. That is, this 12.1.1.0 network segment is a local directly connected network segment. But now I have written a static route. I can artificially configure an address to 12.1.1.0. Such a static route. Now the device on the left goes left. That is, if it believes in this direct connection. It will go left. This device comes out of this interface. This is its next hop. If it believes this static, go right. The device comes out of this interface. This is its next hop. Then, for the same entry network, equivalent to having two directions. If there is a data in the future, match this 12.1.1.0 30-bit mask. Does it go left or right? Here comes the problem. Everyone must be clear. Routing has a principle of adding tables. Optimal addition table. We will compare the priority of forming this route. That is, compare its administrative distance. If the current administrative distance is as small as possible, the device will believe the small. Actually, for different routing types, they're different learning styles. Management distance is not the same. Assume that the left side is directly connected. Static on the right. If it is directly connected, in this table it shows connected. Then its overall administrative distance is 0. For the right, this static administrative distance is 1. Now for the same destination network segment. Now the device only trusts this direct connection. It will add table. While static it does not add table. Although they are learned through different routing protocols. But sometimes you may have doubts. As long as you learn it. Isn't it all right? Why do you have to define it? How did you learn it? Because of different learning styles. Its administrative distance is different. If there is a direct connection and a static, then we will choose direct connection. Because direct connection is definitely the fastest. Is it connected under the interface? But please be careful. Routing protocols and administrative distance. For devices from different manufacturers, they are different. That is, if the two routes we just talked about also appear, then only one will appear in the routing table. It's the direct connection on the left. This is the principle of addition. Compare the priority values of the formed routes. The smaller the value of the administrative distance, the better. Winners will be added. Relatively inferior will be eliminated. That is, it will not enter the routing table. This is the first question. Let's move on to the second question. For us now, our scene changed. Now change the right side to a 24-bit mask. We now have two options. Now both sides are also going to the 12.1.1.0 network segment. The one on the left is directly connected to the one on the right that is static. Then it stands to reason. Definitely better. So we now have to choose. If the future appears in the routing table, do you think it came up? Or does it appear? Or both? Because this is a 30-bit mask. Represents fewer hosts behind. Go left. I have now written a more general. Go right. Which do you think it is? Okay. Both should be added. Assume that the address on the right is not listed. Now both sides are 12.1.1.0. Don't look at the mask. It stands to reason that direct connection is better than static. Because it manages a shorter distance. Now comes a data. This data went to 12.1.1.5. Then 12.1.1.0. 30-bit mask. Variable host bits only have the last two bits. Actually its range is 00011011. Then remove a network address and a broadcast address. It can actually use two addresses. One is point 1. One is point 2. It does not cover point 5. But point 5 is included in the network segment of the 24-bit mask on the right. If you don't understand what I'm saying, that means when I talked about subnetting before, you may not have a good grasp. Need to review after class. To us, In fact, it is covered in the following network segment. If this route has not been added to the routing table just now, that means the data is coming. Just discarded. Obviously the data can arrive, but not retweeted. This misses an address. So for the data, although the part before it is the same, but it masks differently, means it is a different network. Please pay attention. The same network must have the same network number. And the mask is the same. Same destination network. So as long as there is any difference between the two, then it is not the same network. It is a different network segment. All the different network segments need to be added to the table. If the destination network and mask, if the information is inconsistent, we'll add table. If inconsistent, we'll trigger the comparison. Comparing administrative distances forming routes. It is a triggered comparison. We'll have the following comparison. Then we mean. The consistent situation refers to the destination network plus mask is exactly the same. So let's formally discuss administrative distance. It will not happen that the direct connection is on the left and on the right. For example, there is now a direct. It is going to 1.1.2 30-bit mask. Assume that this router interface can only be configured with two addresses. Either point 1, either point 2. This means that an address is occupied here. Then the address on the right. It is impossible to have the same network segment as it. So it can't be a direct connection. That is, under the two interfaces of the router. It is impossible to have addresses in the same network segment. It cannot be both directly connected. So our drawing is also very rigorous. It is a static. Can be configured manually. We can guide the flow. The original data arrives at the destination network segment. This may be a direct connection to the device. But we can then do some bootstrapping. For example, go to other network segments. So, both are directly connected. There is no way to achieve it. Then the addresses under the two interfaces will conflict. There is now a router with a routing administrative distance. For administrative distance, I hope you remember a word. Locally effective. The administrative distance is for a single device. Why is it locally effective? Because the future is in the overall project. You tend to see multi-vendor device combinations. That is, it is impossible for all devices to be from the same manufacturer. This situation will not exist. Because it will involve the safety rating of the project site. It is impossible to use the same manufacturer's equipment. In case there is a bug in its bottom layer. In case it is now system unstable. In case there is a problem with this batch of network equipment. Then the whole project is paralyzed. Therefore, it is often used in combination with multi-vendor equipment. And by cost-effective. So you will see. All kinds of equipment are used together on site. For example, here is a Cisco device. Then on the Cisco device. When I am doing local routing calculations, it is calculated according to your own management distance. If the right end here is another manufacturer's equipment, then it is different from Cisco. That is, for equipment, network equipment from different vendors. The definition of administrative distance is different. So there is no way to compare. Only valid for this device. They made some agreements with each other. Then when calculating, do calculations locally. But don't worry. We have a very large number of routing protocols. Compatible with multi-vendor devices. It does not vary by manufacturer and device model. This leads to problems with the routing table. Although the definition is different. But the final calculation results are almost the same. unless you are in the NP stage in the future. We'll learn some problems that introduce each other. In the NA phase, only remember the local effective administrative distance is to compare the optimal route on the router. Only manage this device. Can't manage other equipment. Okay. Next we will have another concept called cost. For now, you will see marked with an OSPF on it, marked with an EGRP underneath. On behalf of the RA now through a different routing protocol, can learn the route 10. 1.1.0 on RB. If let this router choose, it will definitely choose to go down. Let's look at the form below. EIGRP has a smaller administrative distance. For equipment, it thinks smaller is better. That means OSPF learns this and doesn't want it. But it's not like you don't want it completely. It will be kept as a spare on the device. Actually, it's just unlisted. But this information is still stored locally. If sometime in the future, maybe the following device interface is broken, then based on such a dynamic routing protocol, RA soon sensed that the following path could not be taken. It was originally under the letter and then walked down. But the following device produces a failure. There is a problem with the link. Then go up. This route will be added to the routing table immediately. For data forwarding, it is a spare. That is, if EIGRP fails, OSPF will be added to the appearance. Then go this way on a daily basis. If it has a problem, take the above path. Let's move on to the next scene. For example, now it is not through direct connection. Instead, it is learned through OSPF. Then for OSPF, in Cisco, the management distance is 110. Actually, management distance is also divided into internal and external. I wrote this called external administrative distance. Don't need everyone to master now. Now the device passes the left and right. All learned a 12.1.1.0 route. And all learned through OSPF. The principle of adding tables to routes is, if the destination netmasks are inconsistent, add them to the table. Trigger comparison if it matches. Comparing administrative distance. But now the embarrassing place is administrative distance consistency. Because it's all learned through the same protocol. Admin distance is 110. Now both routes need to add table. We will now have some new parameters. Can come to provide a control. Routing metric. That is the cost we just talked about. So now you will find the same destination network segment. And they come from the same protocol. When learning the same way. Can't compare now. Then we can only choose to compare the new parameters again. Compare route metrics. The route metric represents a cost when the routing protocol forms this route. The smaller the cost, the better. You should know. Different protocols have different calculation methods. So what we're talking about cost. It only makes sense to compare under the same protocol. So if we now compare the administrative distance, when can't compare, we will compare its cost. We look at this picture. They go to the same network segment. How can such a graph be formed? Data should go through this interface. I want to go through this interface again. How can such a picture be achieved? Let's take a look. Now all routes are learned through OSPF. All devices run OSPF. Still a route. Judge or RA. Now the above learned one through OSPF. The following is also learned through OSPF. Then it is now going to the same such a network segment. There are two roads. In theory, you can choose both ways. OSPF is also relatively consistent. At this point we will compare a value called cost. The root metric. It's also smaller. Above is now 20. 10 plus 10 equals 20. Below is now 2. 1 plus 1 equals 2. This 10 refers to the cost of the interface. And OSPF calculates the cost of the outbound interface that sends the data. Make an accumulation. Now the top is 20. Below is 2. Then the following will be selected. That is, choose the one with a small cost value. Data will go like this. When comparing under the same agreement, we'll compare its cost value. If the management distance is the same, we'll compare routing metrics. That is cost. It's also smaller. What if the comparison of routing metrics fails? Look in this picture. The above two are 10. The following two are 1. What if the following two are also 10? This leads to the next question. Data going to the same destination. Two roads are the same. Inside OSPF, cost is calculated based on bandwidth. Inside Cisco, is 10 to the 8th power divided by the bandwidth. Then the result is the cost value. Theoretically, the larger the bandwidth, the smaller the cost value. This is a very good path. Now cost is equal to 10. It means that the cost is greater. Represents the lower bandwidth of the path above. We want to choose the path with large bandwidth. So OSPF route selection is completely correct. Routing based on bandwidth. For different protocols. It uses different parameters to calculate routing metrics. OSPF based on bandwidth. Well, just like we will talk about an agreement today, called RIP. For such an agreement, it doesn't look at bandwidth. It looks at the hop count. So, different protocols use different parameters to calculate routing metrics. Let's take OSPF as an example. If the current agreement is the same, the cost value is also the same. Then these two routes are added to the table. This is the principle of adding table to the route we are talking about. If the routing metric is consistent, at this time, multiple routes will be added to the table. This is called equal cost routing, also known as overall traffic load sharing. Both of them are equivalent in terms of forwarding capability. But here is a caveat. The cost we are talking about now, the route metric, its comparison can only be compared under the same protocol. Because of different agreements, the way to form the overall route is different. That is, different protocols have different ways to calculate the cost value. So there is no ability to compare. For example, there is now a RIP protocol. Cost is 1. The cost in OSPF is 10. The cost of RIP cannot be compared with the cost of OSPF. Because RIP calculates the cost based on the number of hops. OSPF calculates the cost based on the generation width. They are two different protocols in themselves. There's no way to compare them. RIP like a diver. OSPF is like a track athlete. The determinant of a diver's score is splash, speed, beautiful lines, etc. If you get 80 points, a track and field athlete's score determinant is speed, start, sprint, etc. If you get 90 points, then this 80 points and 90 points are not comparable. Because the criteria for judging are different. The same goes for routing metrics. RIP is based on hop count. OSPF based on bandwidth. They are not a standard. It is meaningless to compare such parameters. So, cost can only be compared under the same protocol. Let's summarize the table addition principle. There are two additional table principles. The first is to manage the distance. The second is routing metrics. We are looking at these two parameters.